Let's look at some more examples of sums and products of species. We've seen earlier a species called the subset structure. So P of U is just the power set of U. I claim that P is equal to E dot E, where E is the species of sets. So I'll just give you a visualization of why this is true. So if you have a set, then you can visualize a subset as just choosing some of the elements of this set. So here's an example of a subset. And how can I think of this as E dot E structure? Well, remember that in order to give an E dot E structure on a set U, I need to take the set and divide it into two parts and put an E structure on each part. And so this is just, you just take the first of those two parts and call that the subset. And so this is P here and this is E dot E, and they are evidently the same. I leave it to you to write down a formal proof of this identity of species here. Now let's see what this tells us about generating functions. So let's do the hardest one first. The cycle index generating series. Well, it's just the product of the cycle index generating series of E. So it's just ZE x1 x2 squared, which we have computed. It is exp of x1 plus x2 by 2 plus x3 by 3 and so on whole squared, or if you wish you can think of this as exp of 2x1 plus 2x2 by 2 plus 2x3 by 3 and so on. The type generating series P tilde x is just the types generating series of E squared, which turns out to be 1 over 1 minus x squared, which if you work out is 1 plus 2x plus 3x squared plus so on, saying that there are precisely n plus 1 types of subsets of a set of size n. And indeed the type of a subset is just determined by its cardinality. And so if you have a set of size n, its subsets can have cardinality 0 through n, which accounts for the n plus 1 types. And finally, the exponential generating series for the species P is just e to the power 2x. And this is, of course, summation n greater than or equal to 0, 2x to the power n over n factorial, or we can think of this as 2 to the power n x to the power n by n factorial, which tells us that there are the cardinality of P of n is exactly 2 to the power n, which we anyway knew by other means. We can also try to see what the general coefficient of the cycle generating series is. The coefficient of x1 raised to a1, x2 raised to a2 so we have some finite a1, a2, ak in this exp 2x1 plus 2x2 by 2. This is just equal to, if you think about it a bit, you'll see that it's equal to 2 to the power a1 plus a2 plus ak. Therefore, what it says is that the number of fixed points of a of P of n under a permutation sigma is just 2 to the power sigma 1 plus sigma 2. which is the number of cycles. You should try to think about a direct way to see this. Why is the number of uh, fixed points equal to the number of cycles in the permutation? Okay, now let's try to relate also this to sums. So second claim is that let's let pk of be the species of subsets of size k, be the species of k subsets. So formally I would define pk of u equal to the collection of all subsets of size k. I claim that pk is ek times e, where ek I'm using the standard notation. If it has a species fk is the species where it gives f of u if u has cardinality k and gives the empty set otherwise. So eku gives just singleton u if cardinality of u is k and gives empty set otherwise. Okay, and maybe I'll put to not confuse with powers. And the proof is exactly this picture, except that now this must have k points, and you can only put an ek structure if a subset has k elements. So this will only give something if one of the parts, the first part, say has k elements and the other part has the remaining elements. Okay, but pk, first thing is to note is that p, we looked at infinite sums. Here's a nice example: k greater than or equal to 0, pk. And this is also easily reflected in the equation e dot e is equal to sum k greater than or equal to 0 ek dot e. Well, and then using distributivity you can say that this is sum k greater than or equal to 0 eke, and this is pk and this here is p. But of course you can also prove this quite directly. So what's the generating series for pk? It's the generating series of ek and multiplied by the generating series of e. So what it is it's x to the power k by k factorial summation n greater than or equal to 0 x to the power n by n factorial, which is summation n greater than or equal to k x to the power n, and I can write this as by k factorial n minus k factorial, which is summation n greater than or equal to k n factorial divided by k factorial n minus k factorial times x to the n by n factorial. And so this gives a really nice proof that the cardinality of pkn is given by n factorial by k factorial times n minus k factorial if n is greater than or equal to k and 0 otherwise. Of course, you probably know of other proofs of this, but this is a really slick proof. Now, multiplication of species is associative. So it makes perfect sense to talk about the product of uh, k species. I haven't proved that multiplication is associative, but it's something that you can easily check as an exercise. So it makes sense to talk of f1 dot f2 dot fk for species of structures f1 fk. So we can talk about arbitrary finite products of species, and if you think about it a little bit, the definition amounts to the following. So an f1 dot f2 dot fk structure on U is given by, firstly you divide U into k subsets which are disjoint, partition U into k subsets, put an f1 structure on the first part, an f2 structure on the second part, and so on. An fk structure on the k part. And if I want to describe what transport of structure does, that's as usual, it's the most obvious thing. So if I have S1 is going to be an F1 structure on U1, S2 and F2 structure on U2, SK, then this will go to F1 sigma 1 S1 Fk sigma k sk, where sigma I is just sigma restricted to ui, and this will be a bijection onto its image. So you can think of sigma I as a bijection from ui to vi, and this thing here will again be an f1 dot f2 dot fk structure on the set V if sigma is a bijection from U to V. Let's look at an example of this. So recall that L of U, L is the species of linear orders. So L of U is the ways of putting a linear order structure on U. Which you can think of as functions. Well, okay, maybe we'll come back to that a little later. And let's define Ln of U to be Lu if the cardinality of U is n and empty otherwise. This is the usual definition of the nth degree part of a species. And also recall X, the species X. XU is just U if the cardinality of U is 1 and it's empty otherwise. Okay, in particular, it's obvious that X is equal to L1. Okay, they both have just there's one L1 structure in a set of size 1, there's one X structure in a set of size 1, and there are no structures on any other sets of any other size. And now I claim that X to the power n is equal to L, that these species are isomorphic. And let me just give you a visual proof. I'll let you write down the actual isomorphism by yourself as an exercise. So if you have if you have a set, and here sort of anticipating what I want to do, I'm going to draw my set as a string of points. So now if I have a set I want to divide it into n parts, and on each part I have to put an X structure. So I have to divide it into n parts where each part has cardinality 1. So here's my first part, here's my second part, here's my third part, and so on. And totally they have to be n parts. So here is an example where of an x to the power n structure for n equals 6, and this corresponds to the linear order on a set with 6 points by just saying that this is less than, well, maybe I should say less than, it's strictly less than this, strictly less than this, strictly less than this, strictly less than this. And so there's a bijection between xn structures on U and ln structures on a set U. The set U has to have size 6 for either of these sets to be empty. And so the conclusion finally is that, well, L is summation n greater than or equal to 0 ln. So L is summation n greater than or equal to 0 x to the power n. In particular, x to the power 0 is just the species 1, and this identity here is easily reflected in the generating series L of x is equal to 1 plus x squared. Okay, let's look at another example, the species of ballots. So the species bal k is just defined to be e plus to the power k. What is e plus? E plus is the positive part of the species of sets. So e plus u is defined to be singleton u if u is non-empty, but it is empty if u is empty. For e, e of u would be the singleton empty set, which is a singleton set even if u were empty. But here it is the empty set. So the generating series of e plus is summation n greater than or equal to 1. The constant term is missing, x to the n over n factorial. And so this ballot is the kth power of the species e plus. It's called ballots with k levels. A ballot with k levels is a non-empty ordered partition, is an ordered partition into non-empty sets, into k non-empty sets. So bal k is the species of ballots with k levels. Here's how you could visualize bal 5. So you have a set and you will divide it into 5 parts, 5 levels, let's say. And here ordered means that you, unlike set partitions, the subsets come in a certain order. So you can distinguish between the first block, the second block, the third block, and so on. So this is an example of a ballot structure with 5 levels on a set U. Now let's see if use the theory of species to count ballots. So then finally you can define bal to be the species summation k greater than or equal to 0 ballot k, where you don't specify the number of levels. So right away you see that ballot k of x has generating series e to the power x minus 1 to the power k, and it has type generating series x over 1 minus x to the power k. Right, this e to the power x minus 1 is coming by the fact that the generating series of e plus is e to the power x minus 1. And the cycle index generating series is x of x1 plus x2 by 2, all this minus 1 whole to the power k. This is for ballots k. And for the ballots, you get that the type generating series, the generating series, the exponential generating series is you can get it from here. You get that, just work it out, it's a geometric series here, powers of e to the x minus 1 to the power a, and it turns out to be 1 over 2 minus e to the power x. And ballot tilde x, this is again, you can work it out from here, it turns out to be 1 minus x over 2 minus x. And the cycle index generating series is given by 1 over 2 minus x of x1 plus x2 by 2. So you see, by just understanding combinatorial structures bijectively, you can get species allow you to compute their generating series and therefore count the number of structures very, very easily.